Hello, does this work? Okay, great. Hey everyone, my name's Matt. I work at Uber, and thanks so much for having me here. Before I get started, I want to give you a quick disclaimer. I know a lot of times you go to a tech conference and a big fancy California software company gets up here and tells you about all the amazing things that they built, and I feel like I'm in danger of falling into that stereotype here. And I used to be on the sort of on the audience side of that, and see these people from your Googles and your Facebooks and whatever come up and say, "Oh man, it's so cool! We got all this stuff figured out, and we're scaling to the planet, and they have all these amazing systems." And I'd be like, "Wow, that's weird, because like my stuff sucks. It's like all broken and like legacy, and we're in the middle of all migrations, and like, would be great to do microservices, but it's like." How are we ever going to get this 2 generations old thing migrated to the 1 generation old thing before we even invent a new thing? Well, I'm here to tell you that's how everyone is. Even at Uber, we're that way too. We have all this old legacy stuff, and we wish it was newer. And anyway, that's the reason a lot of people go to give talks at conferences, because they want to talk about their new cool stuff. Meanwhile, back at the office, most people are working on the old legacy stuff. So don't feel too bad. I want to also point out, I don't have all the answers, but definitely we've gone through some fairly unique circumstances, and I hope you can learn something from our experience. So, as you probably heard, Uber's growing a lot. Over the years, we hired a lot of engineers. When I started at Uber about 2 years and 2 months ago, there were 200 engineers. And now there are 2,500 plus engineers. So that's, 10x year over year. That's pretty intense growth. And, why do you hire engineers? When obviously, because you want them to write software. And write software they did. And this is the count of the number of services that we have in production. And I think the really interesting thing about this graph is not necessarily the actual y-axis position, but the slope of that line, showing no signs of stopping. Like once it sort of tipped up, I don't know. I don't see that slope changing anytime soon. So here's sort of some more like gritty details from the observability team about the actual count of services as of like a couple days ago. And as you can see, to my point earlier, most of it is legacy. Like most of it is where it's actually not traced, not measured, not instrumented the way that we would like it to be. I mean, it's not like we have no idea what's going on, but we have some fancy new monitoring tools that we hook up new stuff to, but most of the old stuff does not have it. So as you can imagine, this caused a lot of problems. So adding this many people this quickly, deploying all these new services this quickly, man, it's a lot of issues. Like it's harder to debug this system now that it's broken up into so many small parts. It's harder to profile it. But a curious thing that we're starting to find is we're hitting a lot more friction actually making changes, which is kind of like the point of maybe microservices in the first place, is that it would be easier to make changes. So we'll come back to that. First, really kind of makes, we regularly sort of question this, because we're rolling all this stuff out and thinking, is this, lots of people, whenever they see this graph, internally even, they're like, this can't be right. Like, how can this be? 2,000 is too many. As if there's some number that's like the right number. So I don't know what that right number is, but you can imagine this topic comes up a lot. Like, why? Like, is there some better way to do this? And so we go through the normal set of stuff. Like, okay, so is it easier to release our software? Maybe. Maybe it's easier to release because now you don't have to release the whole thing. If you want to make a change in some small part of it, you can release just 1/2000th of the stack. So that's, probably. I guess that's true. And is it more efficient? Maybe. Maybe it's more efficient because there are some parts that are maybe more compute intensive, and you can sort of scale those independently from the parts that are not. But of course, now you have 2,000 things that are all talking to each other over the network somehow, and there's no way that's as efficient as if they were all in the same process. So I don't know, maybe it's more efficient, but that's definitely not it. Scaling the organization. For us, this is the big one. We could not have scaled the organization, at least at the pace that we did, if it weren't for microservices. So this was really, I think, the only, you can throw all of the other benefits away and still get, as long as we had this one, we still probably would do it. So, I mean, for us, like in our unique situation, like maybe that's good. But so, it's definitely a trade-off, right? Like it's not obvious that this is the right model or what even is the right model. And I think when you really get down to like what the trade-off is that we're making, it comes down to one of coupling. It's like, how tightly coupled are these software components? If they were all in the same giant monolith, which is a thing people do. I mean, like Facebook deploys much of their web service written by thousands of engineers as a single binary. Like the bunch of that front end code all compiles down into like a single thing that runs half of Facebook or whatever. So it's certainly possible that you could build software this way, but we have sort of chosen the far opposite extreme of being very, very loosely coupled. And there are some interesting trade-offs there. One that's really surprising is if the more loosely coupled you are, the more you have your software broken up into individual small modules, the easier it is to engage with open source. So you can publish little bits of your stuff as open source or consume, replace parts of it with open source components. Whereas building it as one giant thing, maybe you would have a little harder time with that. So in case you're thinking, hey, are all of your 2,000 services all just like left pad as a service? We are like, don't you understand libraries? Do you know that libraries exist? Yes, we do. We know libraries exist. We know you don't have to write everything as a service. So these are some stats from our internal Git repo. And so you can see the total number of Git repos in there sort of going up very, very quickly. Now, of course, they're not all libraries. Some of them are configurations that are deployed. They're a deployable unit of configuration. Some of them are just people's personal repos. But 12,000 repos, even if it's a bunch of those, you take out the personal and the configuration ones, it's still lots and lots of repos. So we are way, way down on the down the path of loose coupling, but still there are these services are made up of multiple libraries. And I really wanted to run. Several people asked me like how many lines per service, and I wanted to run this, but I have such limited bandwidth while I'm on this trip, like I wasn't able to pull down all 2,000 things. So maybe I'll figure that out in the future. So, you probably heard, if you talk to people, you see some talks about microservices or whatever, like they're the classic problems that are out there that you'll run into as you're kind of scaling a thing up like this, and these are all problems that we've run into and come up with our own solutions for. And like your databases after a while, sort of like one is like too small, or you want better availability properties, and so you can get some kind of better database, like a Riak or a Cassandra, or build your own sort of sharding layer. And then all these things are talking to each other over RPCs, but it's like if we have a bunch of different languages, so we have 4 languages in production. We have Node.js and Python. We have Go and Java, and so all these things are trying to like pass messages back and forth to each other. So we need to get some kind of RPC framework that allows this cross-language interoperability. So that's a challenge, but tooling is getting a lot better in that area these days, like with things like gRPC, et cetera. Of course, you're going to have all these things got to find each other somehow, so you need to figure out service discovery, and then some slightly trickier ones, like the biggest problems we have with the biggest, or not the biggest, but a common source of things getting overwhelmed is just internal DDoS. Like somebody switches, thinks a timeout is in milliseconds, but it's in seconds, or the other way around, and starts just internal self-inflicted DDoS is the thing that our rate limiter catches more than bad people trying to do bad stuff to us. And sometimes these, we want to support some kind of a graceful degradation as all these things are talking to each other, and sometimes services are broken, and you want to try to cap the impact of a cascading failure. So you want to probably get some kind of circuit breaking, and you want to be able to try to understand this, giant cloud of stuff all as one thing. And so we're going to need some kind of, tracing to, distributed tracing, like a open tracing or Zipkin or whatever to figure out what's going on here. And then somehow all these teams are going to have to be releasing their stuff independently, like whenever they feel like it. And so that's actually a significant amount of tooling to make that process go smoothly. So these are kind of like the generation 1 problems that we've had with scaling our stuff. And it's not that they were easy, but I don't know, we kind of feel good about where we are with all these. But now we're starting to run into some new problems. Like the biggest, like at the highest level, it's just harder to make progress than it used to be. Like it's harder for developers to implement features, to make changes to the system than it seems like it should be. And it's sort of perplexing because you'd think that with all these small little parts all over the place, you could make nice isolated changes and that would be very easy. But one problem is it's really hard to even know exactly where it is you should be making your change. And if you don't understand that, now you end up having to talk to all these different teams and ask them what their thing does, and if you can get involved in their release process and whatever. So let's dig into this a little bit. Like why is it getting harder to make changes here? And I think the way to tell, like the property that I wish we would have, that I feel like we're lacking in our system, is that these microservices talking to each other over RPCs do not compose well. So it's hard to change, to sort of reorder what runs when and who's doing what, and even to sort of understand what these blocks are doing. It's harder than certainly I thought it would be. And by adding that service boundary in between all these modules, we make this, like, we add an extra cost, because like now you're going over the network and it's probably run by some other team, and now you got to do all that stuff. And so let's look at an example. These are real names of Uber services, but the real world is much more complicated than this. And if you work at Uber and you're looking at this, like, I know those arrows don't exactly connect this way. Like I know, but somehow we need less arrows than this, which is how many. This is the dependency graph of the things that are being traced. So then let's like zoom in down to RTAPI, which that was that thing over on the left-hand side of the graph. And up here, we'll find our user service, which is called Populous. Where are you, Populous? There we are. Great. Okay, so that's just the things that, remember that 1,900 or whatever services, and some 800 or 900 of them are traced. That's just the 800 or 900 of them that are traced. Okay, so we clearly can't use that graph. Let's use this simple graph because it's a little bit easier to figure out what's going on. Okay, so what's going on here? So RTAPI is the service at the edge. It's what handles all incoming traffic from mobile phones. The RT is just a historical sort of legacy back when, like, I'm not even sure why we thought we should put that there. It doesn't matter. It's just called RTAPI. And so that's like everything that the mobile phones do, they talk through RTAPI. So then it goes, and this is a scenario where user wants to get picked up. Like someone hits the pick me up button, and this is sort of what happens. So we go to the demand service, and demand service manages a state machine for this instance of this demand, which is like pick me up. And in order to get its job done, demand uses a few other services to do different things. It uses Optic to figure out what vehicle, what products should be visible in that user's area and how much they cost. And then it uses GeoBase to figure out which are the closest vehicles by by haversine distance, and then it feeds all those into Disco, which is a traffic-aware routing engine. So it, of all the candidates that are close enough by haversine, you feed them all into this thing and say, great, how long will it take them to get there? And in general, what are the best ones? What are the ranked list of candidate vehicles that we should select for dispatch? And then in supply, there's another state machine that is the driver. So like the driver has two state machines that are kind of like advancing here by this process. All right, so this is quick little, just to give you a sense of how much stuff is downstream from RT API. Like the big red dot on the left-hand side is RT API. All of the stuff on the right are the things that it goes out and talks to. The size of the dots represent the amount of traffic. The color is some weird, it's a side effect of the only thing that draws a small enough graph that and has a way to take the labels off is our anomaly detection system. And the red, and when I took the screenshot, that just means from that one red dot to that other red dot, something's out of whack. And so you can figure out, like, it's not RT API that's the problem, it's that other red dot down there. If we would show the labels, we could figure out what it was. Anyway, the point is, there's a bunch of downstream stuff from RT API because it's the front end. And so, but it's not all like that. Like this is the downstream for Optic. All the things on the right are what Optic talks to. And so, it kind of gets less and less as it makes its way through the system. Okay, so this is cool. So we've got this, RPC fan out tree, and pretty cool. Like, we're doing it right, microservicing around. We've got our state machines owned by different services, and they've got their own storage, of course, because they don't want to share storage. And they're released by their teams independently, and things are going great. So then the business people come along and say, hey, I got a great idea. Let's launch some new products. This is going to be great. We need to, we're going to route autonomous vehicles. We're going to do Uber Pool. We're going to do Uber Eats. We're going to do all these different things. And then should be easy, right? We already have a dispatching system. Like we already have, like most of the things are the same. Let's just go implement this. So let's take a very, very simple example, because the other ones are a lot harder. Let's say that we wanted to add a new Uber product, which is Uber Puppies. We want to deliver puppies. We're going to have just a car driving around. It's got puppies in the back, and it's like fun. Everybody likes puppies, and you get a car. It still takes you where you want to go, but there's puppies in the back, so that's cool. So interestingly, there are a bunch of different rules that you would have to apply if you're the puppies team. So like you're the puppies team, and everybody, we got all this framework up here, and you're like, sweet, let's get to work. Time to implement our business logic for Uber Puppies. Okay, so what are the rules? Well, turns out the puppies, they can't be in the car for too long, right? Because they have to go out and relieve themselves from time to time. They gotta eat and drink, and just in general, puppies in a car for all day long, probably not a great idea. Further, like we really don't want to take the puppies out to the airport. We don't want them getting out in some neighborhoods we probably don't want to take them to. So suddenly, like we're stacking up some more rules. So you think, okay, no problem. Let's just stick those in. Let's add these weights to the classifiers in Disco, and should be good, right? Well, it turns out that like suddenly you keep running into more and more things that sound very, very simple, but you need to make changes elsewhere in the stack. So now poor puppies team wanted to implement this very simple thing of, we already have lots of different kinds of vehicles, but we want to stick some new rules on there. Suddenly, these changes start propagating up, and next thing you know, you got to go all the way out to the user, because turns out some users don't like puppies. They're allergic, or they're just, I don't know, they're just bad people. They just don't like puppies. And somehow you have to be able to reflect that. You have to be able to say like, okay, we wish we would dispatch you a puppy's car, and the user says like, sorry, I'm not into it, and then we're like, okay, cool, we'll move on to the next one. Well, now, next thing you know, we have changed like everything. And these changes, I mean, obviously we didn't change everything, but we had to touch everything. And these changes are very expensive because the Poor Puppies team is probably just a few people, and they got some cool graphics, and so they got that going. They got 1 or 2 engineers that are like, yeah, no problem, I'll just write a few lines of enforcing these rules. Next thing you know, they have to coordinate the release cycles of all of these teams. They had to go through and say, hey, demand team, can we get that change in? Like, when can we do it? And they're like, really, for puppies? Because like, we're kind of running this global, serious transportation business over here. You want to stick your puppies thing in? Like, I don't know. We'll get it eventually, but it just like, it's tough because like they're always more important. Something that always seems more important than these other features. But like, I pick puppies as like a toy example because it's sort of easy to get your head around. But this happens a lot in a lot of different ways. Changes within that happen to be scoped within a single service end up being great. Like the teams can move independently, they can release independently, and then that's super cool. But if there are ever cross-cutting changes, and it turns out there are always cross-cutting changes. Like no matter how you draw the boundaries, there's always something eventually. Someone's going to come up with something that they hadn't thought of before that you want the system to do, and it's not going to be all contained into one service. So again, I think the problem here is that these elements are not composable. We can't sort of move the lines around and like a Unix pipeline where we can't just add another thing in the middle of the pipeline and not without changing either end the things on either side of it. We had to do all these complicated releases and change our RPC endpoints and all this different stuff. So what most people say at this point is, haven't you heard about events? Don't you know that like things like message queues exist and that you can just put events on queues and subscribe to them? Like, wouldn't that be better? And indeed, we have. We have, in fact, a whole parallel universe of microservices or other event-based things that are on that side. The 2,000 services are largely in the left column of things that talk to each other, mostly with RPCs. But there's a whole other set of stuff that's event-based. This is, for example, how surge works. So there are things that subscribe to the supply events and the demand events, and they compute the ratio of in each of these hexagons around the world. A bunch of other stuff that works that way. But by far the most code that we have is in the left-hand column of things talking to each other with RPCs. And largely, you could characterize it all as things that have to respond while a person's waiting for it. So like, person hits a button, and we need to give them back some response because they're sitting there staring at their phone, wondering when the thing will happen. And everything on the other side is asynchronous, like very, very different SLA. But I think we'll see. Even if we had done all of this as events, I'm still not sure that solves all of these problems. But just so you know, we do have those two worlds, but I'm mostly talking about the RPC world. Okay, cool. So let's talk about like what we're going to actually do to sort of make these things better. So we've got a few efforts underway. They're in various stages of development that are sort of changing this model of like microservices that talk to each other with RPCs. And so the first is around storage. And so, if you're doing microservices right, what you do is you give everything that needs storage its own database somehow, because sharing databases is bad. And I guess it's bad. Like, I don't know, but that's what you're supposed to do. You're supposed to give everything their own database. So here's the dependency graph of Populous, our user service. And so you can see this thing has a lot of consumers. So it's the green dot in the center. Because, as you might imagine, if you want to work with a user in the Uber ecosystem, you're going to need to get that user object from Populous, because that's the service that owns the user object. So it has its own storage, and it has some downstreams too of like, whenever user objects change, we need to validate that these changes are legal with other services down there. But anyway, so you can see like a lot of stuff ends up talking to Populous, and you can see it in that impossible spaghetti graph earlier as well. That a lot of lines converge on Populous. So this is kind of an interesting problem, because you might think, oh, we should just maybe can we just put a cache there? But like, where would you put it? Like, do you put it behind populace? I mean, it'd be nice if all of those things could just talk to the cache and then talk to populace. But like, I don't know, it kind of blows up the model. I mean, I guess you could do it, but we have chosen not to. Populace has its own cache, but still, you've got this kind of focal point of like, really like a lot of traffic kind of, focusing down on this one thing, and that is sort of awkward. It costs a lot, right, to make all these RPCs to this, into this one service. It puts a huge burden on the populace team to sort of like always be up. Like there's no graceful degradation. Like if populace is down, like you can't log in. So that's pretty unfortunate. And there are more problems in the storage domain. Developing against this system is really hard because, so first of all, like you can't spin up the full stack on your laptop if you wanted to. Like there's just no way. Like even if you had one of those like super thick Dell laptops where the battery only lasts 30 minutes, like you cannot put the whole stack on your laptop. And I don't even know that you'd want to. Like it would just take you forever, and it would just you don't necessarily need it, but it is just, that's the baseline. Like you're not going to get the whole stack on your laptop. But then, like related to storage, there's some interesting problems. So how do you work with, as a developer, how do you work with a reasonable subset of data? And so let's say you need like 2 or 3 services to be up just to test your thing. Many of those services might need storage, and so like what are you supposed to do? Like maybe you can get some kind of snapshot from production, or just generate some test data and like hope it's realistic. Yeah, it's complicated. And so we looked at these problems, and oh wait, one more thing, one more big problem. What happens if you want to change the schema? So like your services are talking to each other, and they've got some kind of a schema over the RPC, but there's also some kind of schema to storage, and usually those are similar. And if you ever decide that you want to change this schema, add some fields, change something or whatever, it's a lot more complicated, certainly than I expected. And a big reason is because this. Simplifying that previous graph a little bit, like usually there are a lot more downstream consumers than just your pair of machines RPCing to each other, or one machine talking to one database. Usually these objects end up flowing far and wide throughout the infrastructure and landing in all kinds of different places, message queues and data warehouses and Hadoops and whatnot. So evolving schemas is another big challenge. And so we set about to fix this problem a little while ago, and we had some goals, which were we needed to move past this magic number of services, like 2,000, like what if it was 20,000? Like, I don't know, maybe it will be there eventually, and we got to figure out some kind of an infrastructure where it just doesn't matter how many services you have. But particularly around storage, provisioning new storage should be as easy as checking in code. Like it should just be an effortless sort of thing that you can just do whenever you feel like. And devs should be able to safely work with production data, with real production data, and test their code against this data. And so what do I think like comes next, like for microservices storage? Well, we're working on a project. It's actually in production now. We call it Dosa. It's another fancy acronym. It doesn't really matter what it stands for, but it works like this. Inside of your service, you got a little library, and it turns out behind the scenes that actually makes an RPC over to a Dosa service, and it negotiates a schema at startup. So the service comes up, and it says, I have these objects. I know how to read and write these objects. Is that going to work with you, Dosa service? And that checks with the schema service. And as long as we can interchange our objects at startup time, we can keep exchanging those objects forever. And so even if the schemas evolve out from under us, like we've got a path established, so we can read and write these objects. And we got some Cassandra storage that we put the stuff in, and we replicate it globally or whatever. But the interesting part here is that we allow developers to use this service from their laptops or from their dev instances or whatever. And we do that in kind of an interesting way, which is we've got this RPC gateway, and then we add some context on this, as it admits RPCs to production that come from developer laptops, it makes sure that they're tagged with a context, or this what we call storage scopes. And the way storage scopes work is it gives you kind of a copy on write layer on top of your storage. So here's an example where somebody comes in with a scope list of MJR and prod, and when you do a read, you start reading through the scopes, and as soon as you find an object, you return that one. And so the reads kind of cascade down, and if you get all the way to the bottom and there's no object, then it's not found. But when you do a write, you always write to the topmost scope. And so this works for multiple layers. So like you might have maybe you're working with a team and they've got some fixture that they're all that you're kind of iterating on, but it's not ready for prod, and so you can sort of still as a team share some of this data. It doesn't have to be on a per developer basis. And another interesting thing about this is that it works with these scopes work with the schema service. So you can test out schema changes in your development scope and read and write these objects. You can read the old prod objects and write your new fancier objects into your development scope and decide whether this is a thing you want to eventually release. And the scopes are cheap to create and cheap to drop, right? So if you decide you don't need this anymore, or you made a mistake, you want to start over, you can always drop your dev scopes and just sort of reset them. And so that sort of helps with this pipeline here, because the format that we're storing inside of the Cassandra is a sort of envelope format that has a library that knows how to read and write objects in this format. So the Kafka transits objects that it doesn't necessarily understand. They're sort of wrapped up in this Dosa envelope, and they make their way through to various other things. And so that's pretty cool. We've got that in production like a couple months ago. We're sort of ramping things onto it now. So far, so good. So we get how does this help with the problem of composability? Well, instead of everyone having to explicitly make calls to the user service, now there's a user library. And the user library has these higher level abstractions about things that you can do with users, and it sort of is, we allow everyone to sort of read and write those objects, even if they're not populous. So this is pretty cool. So now we don't have to necessarily have that big burden on the user service. That team works on adding that logic to these libraries. And older versions of the library keep working because all the changes have to be backward compatible. So that's cool. And that's going pretty well. But there's another problem related to storage, especially in the microservices world, which is transactions. So if you remember the picture with the supply and the demand, when that happens, we would really like to do those changes atomically. We would like them to all either work, both work or not work. But when we've got multiple independent entities and they're talking to each other over RPCs, that becomes very complicated. It's hard to do a transaction across a service boundary. And so what comes next? How can we fix this problem? Well, so when we look at this, when you look at sort of from this model, it doesn't seem very possible. Doesn't seem like there are a lot of good ways to go here, and so we're implementing an idea that we got from Katie, who's sitting right here in the front row, and she's given several talks about this. You should definitely go check it out, which is Sagas. Sagas are a long-lived transaction. And the way that this works is you, for every kind of step in the transaction, you propose or you add a compensating action. So if you need to roll this thing back, you can roll it all back with these compensating actions. And some one thing has to coordinate this long-lived transaction. So this is called the coordinator. And here is a very real-world example. I actually didn't show you all the pieces in the previous thing, but the way that this supply-demand thing works is a third entity called job. And you can imagine why we would need jobs if you think about Uber Eats or Uber Pool. a job might get handed around to multiple entities and have many, many more states. So we need to change 3 things. So user hits the pick me up button, and we say, okay, cool. We found our candidate. Everything seems great. Let's do this. Let's actually make this thing happen. And so the way that works is the coordinator sends out an assign to all these things, and assuming that it works, then everybody's great. But if one of them does not work, then we send out the unassign. I mean, this is really, really oversimplified. You should get all of the details if you're interested in this from Katie's talks or whatever. There's some other papers you can read about it as well. But this isn't perfect. There are a lot of edge cases, like what if one of those steps was send a push notification? Like, it's kind of hard to unsend a push notification, right? So the compensating actions are semantically compensating. So you could maybe send another push notification that says, sorry about that, just kidding, or whatever. But so this is kind of a cool thing, because the number of things that need to be done in this form, it's actually really small. Like, most things you can kind of work independently, but every now and then there are times where we need a little bit of coordination across these entities, and Sagas give us a nice way to make that happen. So I think that particular workflow is teetering on the brink of production. We're toying with a few other workflows, but that one is just about live. Okay, so perhaps the biggest problem, I think, with these big microservice architectures, at least as we have deployed them, is that all these entities are talking to each other over RPCs. And these RPCs are not as loosely coupled as I think they should be. They're, in fact, very tightly coupled. Like, service A knows that it's talking to service B. And I think this is a really tricky problem. But the problems with RPCs are vast. And if you went to Chris's and Katie's talk yesterday, you got maybe a sense of them. If you haven't, I would recommend you check that out. Or check out, Chris has this website with a bunch of all the reference materials. The evidence stacking up against RPCs is vast. Clearly, there's something. Maybe there's some room for improvement here. And it's like local computation is fundamentally different from remote. That's true. I don't actually think that's the real problem that we have. I think we've got some different sort of challenges with how do we actually to meaningfully compose these event handlers in a way that allows these cross-cutting changes to be done more easily. So what do I think that world looks like? This is an area we're kind of into the bold new future of things we haven't actually implemented yet, but we're just trying to, we're in the early stages of designing. And I think, okay, first of all, obviously asynchronous message passing, better than, I get it. That's clearly the future. The RPC model has, some fundamental challenges, but it requires, I think, a little bit a different way of thinking about what it is we're trying to accomplish, and I think why we're trying to accomplish it. There is this great quote on that Chris has from this Steve Vanusky paper that I think is really relevant here, which says, does developer convenience really trump correctness? All these other bad things? And the very, very next line is, of course not. No way. There's no way it's worth it. And I'm not sure that that's always true. I think it's often true, but I think that there are cases where developer convenience might actually be a thing that we ought to optimize for. So I think the world we want to live in is not this RPC world where RT-API knows it's talking to demand and that knows it's talking to Optic and does all these things. I think we want to live in a world where demand has some way of emitting some event that it will for sure get exactly one response to that says, hey, what vehicles are closest? Like, will someone figure this out for me? And some entity, make sure that that does get handled within the right SLAs to respond to users who are waiting for these answers. And likewise, it could emit another event that says, like, which vehicles have the lowest ETA? And that gets handled in a request response manner, like, that meets the SLAs that we're looking for with graceful degradation and all those things. But it didn't explicitly send it to the Disco service. It just said, I want to know this thing. And then likewise, so if we live in this world, we could do a really cool thing, which is if you were the puppies team and you were like, I want to implement the puppies product. We got to add some business logic. Where do we put it? What you could do is stick your little orange box right there in the flow and just hook in without changing the Disco service or without changing any of those classifiers over there, and just add your logic completely independent of those other teams and say, wait, I gotta get a crack at this before this thing flows back. I need to make sure that the user actually likes puppies. Because if the user doesn't, we need to actually reject this, reject this candidate and move on to the next best one. But right now, this is the problem with all the red dots. This is like, in order to implement that, we had to end up touching all these different things, and that was really, really painful. So we'd like the teams to be able to make these changes to insert these logical blocks without having to re-release the other, the peer blocks in this flow. I think that would be pretty great, but right now, there's kind of no way to do this. Like, there's no way to do this that sort of works as seamlessly. Like, you can kind of get at this a little bit, but there's always like some horrible trade-off around your SLA or I don't know, just cost in general. But so this world like that I think we want to live in is more along the lines of what I'm calling composable event processors. I think this is a reasonable or a better model for deploying microservices at scale. Is instead of services, we have these event processors and we have some orchestration layer to tie them all together. And so that's pretty cool, and you might think like, wow, isn't that like the same as workflow, or isn't this like AWS Lambda or whatever? And yeah, kind of. I mean, there are elements to that. And I think realistically, I think Amazon will get there eventually. I mean, if you look at the pace that they're rolling out new things, it is inevitable. I think that soon there will be an Amazon composable event processor service you can subscribe to, and it will be great. But I hope that we as an industry can develop a vendor-neutral alternative, because there are many companies for whom the Amazon solution will not be acceptable. And I think in general, we would all be better off if there was a neutral, kind of vendor-neutral way to do this. So you really have to ask though, like why am I up here talking about changing the fundamental, paradigm of, back-end computing? Like I work at a transportation company. Like I'm not work at a future of, inter-service communication company. Like why does any of this matter? And I think that the reason is because the tools that we have to work with, the tools when we were just getting started, they're very different and the requirements are very different from the tools that we need when things have scaled up, and not that many people have scaled up. And so there are a few companies that end up having to just grapple with these sorts of problems. But the world that I want to live in is one where we make the tools for building big be better than the tools for building small. So we don't have to make this kind of transition. Like if things scale up, then you're like, oh, I have to re-architect and now I got to get my message bus or whatever. But what if when people started, it was just better and obvious because their tools gave them safe access to production data or these, all of these other properties that even when you're small are actually pretty useful. And so you go back to this quota, this scathing indictment of the RPC model. I really think that the answer is, at first, it does. Like at first, developer convenience is actually the only thing that matters. I think most software, most startups fail. A lot of software ends up not working. It turns out to be a bad idea. At small scale, developer convenience is the name of the game. So we need to build tools so that at small scale, things are just better even as they scale. I think a way that we can tell if we are there is to look at how composable these things are, and maybe take the puppies example and see if we could implement that kind of change without re-releasing the components on either side. Then I think maybe we're there. And that's all I have. Thanks a lot.